Sanderson from New Mexico State, who's going to give the last talk of the symposium about radio galaxies with extended gas reservoirs in the redshift range 0.2 to 0.6. Take it away, Kelly. I'm going to change my background. We see everything, so you're good.
Okay, cool. Thank you. Hi, I'm Kelly. I'm a rising fourth year graduate student in the astronomy department at NMSU. And I've been using data collected on APOSS 3.5 meter telescope using the long slit spectrograph disk, which many of you by now know stands for dual imaging spectrograph. The purpose of these data is to assist in investigating the nature of radio galaxies hosting extended gas reservoirs at intermediate redshifts. By intermediate redshifts, I mean redshifts between 0.2 and 0.6. And for those of you who don't speak in terms of redshift, this corresponds to when the universe was like 10.3 billion years old. My advisors for this project are Dr. Maura Prescott from New Mexico State University and Dr. Anna Kopinska from the National Radio Astronomy Observatory in Sapporo. Okay, so here's a brief outline for the structure of the talk. I'm going to give you guys a little bit of background on what radio galaxies and extended emission line regions are. I'll provide some details about the project that I'm working on, some results that we've found so far, and then end with a summary of the future work needed to be done. So for background, it's believed that all galaxies contain a supermassive black hole at their center. In some galaxies, these supermassive black holes are active, meaning that they're consuming material from the galaxy. And this material is causing them to emit a lot of radiation or a lot of energy, either in the form of powerful radiation and or energetic particles. These galaxies with active supermassive black holes at their center are known as active galaxies, and radio galaxies are just a subclass of active galaxies that are bright at radio wavelengths, as you can guess from the name. This radio emission that makes them so bright at radio wavelengths is coming from the energetic particles being driven or accelerated rather out of the galaxy, and this acceleration is causing these particles to emit synchrotron radiation in the radio band. These sources can also be called jetted AGN if the radio emission is in the form of collimated jets. So this picture that I'm pointing at right now on the right is just showing a composite image of an active galaxy where you can see that powerful radiation I was talking about from closer into the host galaxy, and then also the energetic particles being driven out into the environment of the entire system. And so these active sources represent a unique and specific phase in the evolution of galaxies, and so understanding them is important for galaxy evolution because the power produced by the AGN has the ability to influence not just the host galaxy that it's in, but also the environment that the host galaxy and AGN both reside in. Extended emission line regions, or ELRs, are extended reservoirs of ionized gas that reach out to tens of kiloparsecs from their host galaxy and into the CGM. These ELRs are generally found around active galaxies because the energetics emitted by the AGN are powerful enough to illuminate the gas via ionizations. These sources are typically associated with jetted AGN, or the radio loud ones, although samples of non-jetted AGN hosting these extended emission line regions also exist. An example of these non-jetted varieties would be like most of the green beam galaxies that Maura was talking about in her talk on Monday. Oftentimes we can also see, or sometimes we can see kinematic signatures of the AGN within the lit up and extended gas, either in the form of outflows or shocks or just general interactions. And so studying these extended emission line regions provides insight into the fuel necessary to grow galaxies, the energetics that are released from these host galaxies and the AGN, the effects of galactic scale feedback, and the characteristic timescales over which this feedback is occurring. But two things about extended emission line regions that are not always obvious and that I'm interested in looking into are what is the origin of this extended gas that we're seeing lit up? Is it gas that was part of an outflow from the host galaxy or remnants of a past merger event or something else? And the second thing that's not always clear is what is powering the gas to glow. So while the energetics of the AGN are usually assumed to be the culprit, it's not always clear if it's mechanical energy or radiative energy that's causing the gas to become ionized. And so the goal of this project is to conduct an investigation into both the AGN and the extended structures surrounding them at intermediate redshifts in order to further understand the nature of these objects. So specifically, we're aiming to answer the following questions. Like I previously said, what is the origin of the extended structure that we're seeing? What is currently or what was powering the extended emission? And what are the timescales associated with the powering mechanism? The project's broken down into two parts. So part one, we're aiming to identify a sample of jetted or radiolab type 2 AGN hosting oxygen-3 bright extended emission line regions at these intermediate redshifts. And then in part two, this is where we will study the properties of these extended gas reservoirs and of the host galaxy and AGN to hopefully gain insight into their nature, origin, and powering mechanisms. So to accomplish part one, we're relying on a heterogeneous sample of 51 radio galaxies that were selected to have high resolution broadband radio imaging taken for them. The sources in this sample were selected as likely having extended radio emission and strong optical nebular emission, and they were selected by citizen scientists participating in a radio galaxy zoo forum. And essentially, this group of citizen scientists and the scientists leading them were looking for jetted AGN that had green bean galaxy-like properties. So if you recall Moore's talk, these are basically type 2 AGN with extended oxygen-3 emission. But in this case, they were looking for ones that were associated with jetted radio emission as well. However, upon further investigation of the archival optical and radio images from SDSS and FIRST for this sample, it's clear that not all of the sources that were selected to have high resolution radio observations taken actually meet the criteria of having both extended oxygen-3 and jetted radio emission. There are plenty of them that don't have these criteria met. So part of this project is to figure out a way to select sources from this sample of 51 galaxies that do meet those criteria. And so to do this, for the 51 sources that we have radio data for, only half of them have existing archival SDSS optical spectra. So in order to get at selecting sources with strong oxygen-3 at the redshift range that we're looking at, we started a redshift campaign to collect low resolution optical spectra for the remaining half of the sources, and we've been using DIS on the 3.5 meter to do this. These optical spectra serve three main purposes. They will allow us to constrain the redshifts of the sources that didn't have SDSS spectra. They'll allow us to select which sources meet our criteria of having strong oxygen-3 emission that is also extended. And then lastly, they'll help us characterize the properties of the gaseous halos, which leads into the second half of the project. Once we've used the spectra to identify a sample of sources that have strong oxygen-3 emission extended and at the right redshift range, we can use the previously obtained spectra to also estimate the physical conditions of the extended gas and in the host galaxy. And by physical conditions, I mean things like electron temperatures and electron densities. We'll also use the existing radio observations to characterize the radio morphologies of these sources, map out their magnetic fields, and also determine the age of the particles that are emitting the radio emission or the radio synchrotron. And I'll talk a little bit more about what I mean when I say determining the age of the particles on a later slide. So in terms of progress on this project, over the past year, we've collected APO DIS spectra for the 25 sources that didn't have the archival SDSS. And this allowed us to determine which sources are falling into that intermediate redshift range. So after removing 6 sources that were either too faint in the optical or were outside of the redshift range, we were left with 45 sources with redshifts between 0.12 and 0.6, as seen in this figure to the right, which is just showing a histogram of the redshift distribution for that remaining sample. As mentioned previously, these spectra also allow us to identify which sources have strong oxygen-3 emission. And so while the analysis of the spectra for this purpose is still ongoing, I've selected 2 sources that I just wanted to highlight for the purpose of this talk. So for each source, I'll display the composite SDSS optical image on the bottom left, and then the extracted 1D spectrum from APO on the top right, and the raw 2D spectrum on the bottom right. And so for this source that I'm showing right now, this is our prototype source for this project. It was serendipitously discovered by my NRAO advisor, Dr. Anna Kopinska. And it was the first, or one of the first jetted AGN that hosted an extended emission line region at these redshifts that we were introduced to, and that got us thinking about these types of sources. So that's the first one that we started working on, and that's why we're calling it our prototype. So the postage stamp image is showing the bright green colors of the source, which are due to the strong oxygen-3 falling into the R band through the SDSS filters. The 1D spectrum is showing multiple emission lines that are super interesting, like oxygen-3. So we have strong oxygen-3 like we were searching for, but there's also Balmer emission lines like H-beta and H-alpha, and then emission lines like N2 and S2, which will be useful for diagnosing the conditions in the gas. And then what's really interesting is the raw spectrum. It seems to be showing some kind of detached oxygen-3 emitting blob. Oops, sorry. Which we're interpreting as possibly a signature of an AGN outflow in this source. And then this other object is also really cool. It has a lot of the same emission lines in its 1D spectrum, but I really like looking at the optical morphology and the 2D raw spectrum. For this source, you can see the bright green colors again, indicative of the oxygen-3 captured by the R band. And this emission seems to be in the shape of a biconical structure, which could be telling us something about the distribution of the gas or something about the geometry of the AGN. And then also in the 2D spectrum, it's really cool looking. I love looking at these images. This one is this is the oxygen-3 emission, and it's showing a lot of clumpy and extended looking emission, possibly signifying an AGN outflow or some kind of interaction between the AGN and this extended gas. So back to that first object I showed, the prototype, we also made progress reducing and imaging, the radio data for this source. And this is shown in this first image where we have the radio contours from C-band imaging overlaid on top of the optical R-band, which again is capturing that oxygen-3 emission. And this allowed us to characterize the radio morphology as being extended and having at least one classical FR2 radio lobe. But we're not really sure why it's asymmetric and that this lower structure is not a classical FR1 or FR2 radio lobe. For this source, we've also identified evidence of an aging particle population in the core. So this is what I was talking about when I said we were interested in determining the age of the synchrotron emitting particle population. This aging that I'm talking about is seen as a curvature in this radio SED. So on the x-axis, we have frequencies between 5 and 11 gigahertz. The y-axis is the flux density in millijanskys, and this is for the core component, which is shown here by this green dot in the contours. And so this curvature that you're seeing is caused by the higher energy synchrotron emitting particles decaying faster than the lower energy or lower frequency synchrotron emitting particles. And this is just something that happens when you have a population of synchrotron emitting particles that aren't being replenished or continually accelerated. The ones that are radiating away more energy will radiate away their energy faster. And it appears as this curvature or steepening of the SED slope. And you can model this to kind of back out an age since the last time this particle population was replenished or accelerated by the AGN. And this is basically signifying variations in the energetics of the supermassive black hole powering this emission. And so just to wrap up, we're halfway done with phase 1. We've basically obtained all the optical APO spectra that we need at low resolution. So we hope to complete phase 1 by the end of the fall semester, and then start phase 2, which is where we'll basically be studying the properties of the extended emission and the AGN and host galaxy, and hope for that to be completed as part of the thesis by spring 2023. I'm sorry for going over a little bit. Just wanted to say thank you to the Science Symposium Organizing Committee for putting this symposium together, my advisors, Dr. Prescott and Kopinska, my fellow grad student, Audrey Dijot, who's been helping me collect and reduce the spectra, and then the, of course, APO observing staff for being so helpful every time I'm at the telescope.
All right, thanks, Kelly. All right, thanks for all the speakers for great talks for this final session here. Any questions for Kelly? Still no. Oh, I got a hand. Go ahead, Bryson.
Sorry, quick one. On that the last little plumpy green bean you showed, do you remember? Yeah. Do you know like what angle you had the slit, how that was arranged? Like, what are we looking at here?
Yeah,
That way?
it was angled like at the same angle as that bicone, and also which happens to be the same angle as the radio axis for this source.
Ah, cool.
All right. So, and again, you can continue to ask questions on